In this section, we're going to kind of get away from the ideas of sequences and series for just a little bit, and we're going to be looking at approximating functions with polynomials. So basically what we have here, let's say we have a function f of x equals e to the negative x. Transcendental function. This one's not so difficult to integrate and take a derivative of, but imagine taking 10 derivatives of this or integrating it several times. Transcendental functions, trig functions, square root functions, any radical functions are difficult to work with. So what we want to do is we want to approximate this with a polynomial function. Now what we mean by a polynomial is something with powers. So for instance, it could have something like x squared plus 2x plus 1. It could have x cubed plus 7x squared plus 2x plus 1. So again, when we're talking about a polynomial function, we're talking about where it has integer powers. Now there's a specific thing that we call this, and it's called a Taylor polynomial. And there's also another one called a Maclaurin polynomial. But this book isn't too specific about those at this point. But I'm going to be referring to these as Taylor polynomials. Now with the Taylor polynomial, basically it's saying if we have some function f that has n derivatives, meaning we can take as many derivatives as we need to, and we'll get into this idea of what n actually means, and it's going to be centered at a particular value. And we're going to call this generic value c, and I'll show you what this looks like graphically in a little bit. Then what we know, the polynomial function that does the best job of estimating this function is given by p n of x. So here's n. So that again, n derivatives p n of x. This is basically giving me the highest power of the polynomial. So if I'm talking about an x to the fifth, that'd be a fifth degree polynomial, and this would be p5 of x. So what this looks like then is my original function evaluated at its center plus the first derivative of the function evaluated at the center times x minus c. And then this pattern keeps continuing. The second derivative of the function evaluated at its center times x minus c. Now it's second derivative, so now I have the second power on the binomial, and this is divided through by 2 factorial. Now just to stay with the trend, this is actually to the first power divided by 1 factorial, and this is, I guess if you wanted to write it, it would be x minus c to the 0 power, but anything to the 0 power of course is 1 over 0 factorial. So you can see the pattern here, and you can see where we're going to be turning this into series very shortly because there's a distinct pattern. Let me go ahead and rewrite this just a little bit to include that so it doesn't look like it's an exponent. Okay, and so again that was x minus c to the 0, anything to the 0 power is 1, plus the first derivative evaluated at its center, x minus c to the first over 1 factorial, plus the second derivative evaluated at c. c is the center, and I'll explain what that means here in a little bit, over 2, so the second power over 2 factorial. And this pattern will continue. Here I have my third derivative evaluated at the center, x minus c to the third over 3 factorial. And this pattern will continue until I get to my nth power, or my nth derivative. So this is fn, and this is n for the value of my derivative evaluated at its center, x minus its center to the nth power over n factorial. So we can definitely see that there's a pattern here, and we'll definitely be looking at what to do about this pattern as we work on a little bit further. Now there's a couple things we want to see here. This piece n of x is called the nth Taylor polynomial. For my function f centered at c. So if I was looking for, let's say something like a higher degree polynomial here, I might be looking for a 5th degree polynomial. If I was looking for the 5th degree polynomial to do an estimate, I'd be looking at p5 of x. and I'd be looking at taking 5 derivatives. So whatever you're looking at, you have to be able to take those 5 derivatives then. And again, these can get pretty out of hand if we're looking at product, quotient, chain rules, that type of thing. Now let's go ahead and look at a graph to try and explain kind of what we're up to here. Now specifically, I want to look at a graph, e to the negative x. So this is the graph of e to the negative x that you see right here. What I want to do is I want to estimate this at its center, and the center is going to be equal to 0. And I want to estimate this with a polynomial function because polynomial functions are easier to work with in terms of integration and derivation. So I'm not going to go through the steps on how we find these quite yet, but I just want to give you a look at what we have here. The first best estimate that we could have for a 0-degree polynomial would be y equal 1. And so that's my best estimate. That's this point right here. Now as I go to a 2nd-degree polynomial, my estimate turns out to be 1 minus x. So that does even a better job. So let's kind of blow this up a little bit. See how this orange line, it is good at estimating right here, but it's not very good at anything close by. So 1 minus x definitely does a better job of estimating this red line right here at 0 than the orange line. Let's go ahead and look at a 2nd degree. Now remember, this is a 1st degree because the power is 1. Let's look at a 2nd degree. And again, I've already done the work to figure out what these are, and I'll show you what that work is, but we just want to look at this pictorially. So 1 minus x, so I'm expanding 1 minus x plus x squared over 2. Now if you notice, orange does the worst job. I'm trying to approximate this curve, and I'm trying to approximate this curve at its center, and in this particular case that center is right here at 0 and my y value is 1. So you can see the orange job does a really bad job. I'm going to turn that one off because it's not as useful. It looks like to me that this red line comes in and does a pretty good job, and so does the black one. And then this line right here, this underlying line right here, is my actual function. So actually let me come in and change the color of this one, if it will let me. I guess I can't change it right now. But we can see that it's doing a little bit better job. So this is the graph that I'm trying to estimate. It looks like the straight line doesn't do such a great job, but this red line does a very, very good job right near that center. It looks like I can come out almost pi over 6 units and do a very, very good job estimating. So again, these are all my lines. I have a 0-degree polynomial, so let's start from the beginning. I'm trying to estimate this orange line. Okay, so let's go ahead and look at our 0-degree polynomial first. So again, this orange line is the curve I'm trying to estimate. Now I know I can't estimate it at all points, and so I have to kind of choose where the points are important to me, and I'm choosing that center here at x equals 0. So my y equal 1, it definitely does a great job, but only right at that exact point. Now if I go to a 1st-degree polynomial, I can see that it does a little bit better job, meaning I can look at a couple points beyond this a few points on either side, and it does a very good job estimating. Now if I go to a 2nd-degree polynomial, it does a really good job. This is that purple line. You can see I can come clear out to here, and it's doing an excellent job at estimation. So the idea here is a couple things. First of all, what's the highest power I need to go to come up with a really good estimate? Because I don't want to have any higher powers than I have to, because there's a cost to that, and the cost is basically more terms, more difficulty working with. So we want the fewest number of terms that does the best job possible for what our particular needs are. So the way we're going to do this is we're going to come up with some approaches to come up with these Taylor polynomials, and then we'll also look at error, how much error is introduced into the process to estimate these. Now the process here, we'll look at graphs again a little bit later, but the process here is very algorithmic, meaning it's very repetitive. I do the same thing over and over again. So what I'm going to do is I want to do, let's do e to the negative x, just like the one that we were looking at. So we want to find the linear approximation. So that's going to kind of be my part 1 here. And I also want to not only find the linear approximation, but find the quadratic approximation. And then let's go ahead and go out to P4 of x. And of course we're going to have to find P3 of x in between. But that's okay, we can work on that along the way. So find the linear approximation, quadratic approximation, and P4 of x for f of x equals e to the negative x. And let's go ahead and be centered at 0 here. So the formula that we need is right up here, this Pn of x, and it's just going to be this process. So the way I usually work these is I try and create a chart. The chart helps me keep track of what I need. So I'm going to start with derivatives. And then I'm going to look at what the center is, and the center is the same all the time. And then I'm going to be looking at the derivative evaluated at the center. So evaluated. Now a couple of things that are happening here. If I'm looking for the highest is the 4th degree polynomial, I need to be able to take 4 derivatives. So let's go ahead and start with my original function, f of x equals e to the negative x. F prime of x equals negative e to the negative x. The second derivative of x is equal to e to the negative x. Third derivative is negative e to the negative x. And then the fourth derivative, and sometimes you use the Roman numerals when you get past the 3, so iv of x equals e to the negative x. Now this derivative is pretty straightforward to take, but if you had a product rule, quotient rule, chain rule, you'd need to be able to show your work on those. Now the center for each one of these is the same. Now again, I'm trying to come up with a polynomial that estimates the function e to the negative x near x equals 0. So basically I'm plugging in e to the negative x, I'm plugging in a 0 here. So f of 0 is e to the 0, which is 1. Then I have f prime at 0, so that's going to be negative e to the 0, which is negative 1. And you'll see a quick pattern here start to develop. So this would be e to the 0, which is 1. So this is going to be negative e to the 0, which is negative 1. The fourth derivative, e to the 0 is 1. So these are the important things that I need here. The first one we're going to be looking at is my linear. So let's go ahead and look at P1 of x. Remember in the directions we were asked to find the linear approximation. So linear would mean the highest power is 1. So that would be P1 of x. So P1 of x, and again I'm just going right up here and I'm following this formula, would be f of c times x minus c to the 0 over 0 factorial. And of course that's my formula written out. We're actually going to plug in values here. So that would be f of 0 times x minus 0 to the 0 over 0 factorial. F of 0 we know from up here is 1. X minus 0 is just x to the 0. Anything to the 0 power is 1. And 0 factorial is 1. So P1 of x is just equal to 1. Now again, this is my linear approximation. And the reason it's a linear approximation actually this one would be my constant approximation. I should be careful how we say that. And this one would be my constant approximation because I don't have a first power on my x here. It does create a straight line as well, but we'll call this the constant approximation. And so this would be P0 of x because my highest power of 0. So let's get my notation straight here. Okay, my next one would be P1 of x. There's my linear. So this is going to be f of c x minus c to the 0 over 0 factorial plus f prime at c, first derivative, p1, x minus c to the first over 1 factorial. And again, all I'm doing here is writing out my formula first and then populating the formula by the values from the table up above. And I think this is a really good idea because it kind of makes sure that you keep track of all your values. Now this piece we already know. This piece is right up above, is just equal to 1. Now this second piece, f prime at c, would be f prime at 0 times x minus 0 to the first over 1 factorial. So we're continuing to simplify. P1 of x is equal to 1. That's the first term. Plus f prime of 0. If we look up f prime at 0, we see we have a negative 1 here. X minus 0 is just x, so I have x to the first, and 1 factorial is just 1. So P1 of x is just 1 minus x, simplified. Now this is my linear approximation. Now the reason it's linear is the highest degree on the exponent for my variable is 1. So it creates a straight line. Now again, up here, this creates a straight line as well. This is just y equal 1, but this is a constant, whereas this line has slope to it. So there's P1 of x. Let's go ahead and look at our quadratic, P2 of x. That's just going to be basically P1 of x, meaning my previous P1 of x, plus the second derivative. But I'm going to go ahead and write it out. So I'm actually going to change the color here so we see the change. So this is P2 of x is equal to f of c x minus c to the 0 over 0 factorial plus the first derivative evaluated at its center, x minus c to the first over 1 factorial. Now I have my second derivative evaluated at its center, x minus c quantity squared over 2 factorial. Now the reason I keep writing this out over and over again is pretty soon we're going to have to start seeing a pattern here, and it's easier to see the pattern if you see it written out. If you skip any steps, the pattern is kind of harder for it to materialize. So P2 of x is equal, we know from up above, fc x minus c to the 0 plus the first derivative, this group right here, this is just equal to P1 of x. So that's just equal to 1 minus x. Okay, plus the second derivative evaluated at its center, that would be right here. So that's going to be 1 x minus 0 quantity squared over 2 factorial, and 2 factorial is just 2. So what this ends up looking like then is P2 of x equals 1 minus x plus 1/2 x squared, because x minus 0 is just x quantity squared. Now this is my quadratic approximation, the second degree polynomial. Okay, so now the next one we jumped to was P4, I believe. So we can do P4 without doing P3, but I guess P3 is embedded. So I'm going to just go ahead and write out P4, and we'll see where P3 comes from as well. And again, this is going to be basically P1 plus P2. Actually, that's not quite right, because if you had P2 of x, you'd have P1 written twice. So this is really P3 of x plus the fourth derivative evaluated at center times x minus c to the fourth over 4 factorial. So in order for us to figure out what P3 is, if we want to take that shortcut, if we already knew it, we could just write it down. That would be equal to P2 of x plus the third derivative, x minus c cubed over 3 factorial, plus this last term. The fourth derivative evaluated at center, x minus c to the fourth over 4 factorial. So because we skipped P3, I had to rewrite P2 plus that third derivative to help us figure out what's going on here. So I have P4 of x equals, now P2 of x, I already know from up here, is 1 minus x minus 1/2 x squared. So this bit right here is P2 of x. Now this is going to be plus my third derivative evaluated at 0. So we come up here. Here's my third derivative, and if you notice our signs are alternating. So that'd be a minus 1. Now this is x minus 0, which is just x, so negative 1x cubed over 3 factorial. 3 factorial is 3 times 2 times 1, and of course 1 being the multiplicative identity, I don't need to include that. Okay, so next I have my fourth derivative evaluated at center. So you can see my fourth derivative evaluated at center is 1, so this is plus 1. X minus 0, because my center is 0, would be x to the fourth over 4 factorial, which is 4 times 3 times 2 times 1. Well, we have some simplification to do here, so P4 of x is equal to 1 minus x minus 1/2 x squared minus 1/3, not 1/3, minus 1/6 x cubed plus 4 times 3 is 12 times 2 is 24 x to the fourth. So this is my polynomial. This is my fourth degree polynomial that does a really good job of approximating e to the negative x. Now, not right now, but soon, eventually, we're going to start looking at this. And we're going to say, oh, that's a series. It's an alternating series with values that go positive and negative. So I know I'd have a negative component here. And then it looks like to me, my factorial, this goes 0 factorial, 1, 2, 3, 4 factorial. So I'd start at k equals 0 to infinity, and my denominator would be a k factorial. And it looks like my exponent would be 0, 1, 2, 3. Okay, that looks like it works. So that would be x to the k. Now this is my series, and I'd have to test this series, and I'd find a radius of convergence, mean how far can I be around that center and still be a convergent function. So eventually, not right now, but this is what we kind of want to be thinking about. So that's why it's so important that we write all these out and show our work. Now getting back to the graph that we were looking at, I don't have this one entered. Let's see if I can copy and paste this. Guess not. So let's go ahead and enter that fourth degree. So 1 minus x plus x squared over 2 minus x cubed. Oops, that's not quite what I wanted. Plus x squared over 2 minus x cubed. And this x cubed will be divided by 3 factorial. I don't know if I have a function here for factorial. Yeah, I do. So let's put in that 3 factorial. And then plus x to the fourth over 4 factorial. Now if I wanted, I could actually write out the 3 factorial being 6, etc. But again, there's an advantage to being able to see some of these patterns. So I don't think it's such a bad thing to leave it in factorial notation. Okay, so what we have then, I'm going to get rid of all these smaller degree polynomials. And we can't really tell, but there's the red line under here. And so again, the graph for the red line is e to the negative x, and we want to do the best job that we can about approximating this at x equals 0. And so if x equals 0, we know we're up here at y equal 1. So let's see what does a really good job with that. Let's do a dotted line here. Now it's really hard to see. Let's see if we can get it to show up a little better. But we can kind of see all these little black dots here? This is the graph of that fourth degree polynomial, and look what a good job it does. It does a real bang up job. It looks like until we get to a little over pi over 3 positive, and gosh, on the negative end it goes up quite a bit more as being a good approximation. I would say clear up here maybe into negative pi over 2. So we can see that that fourth degree polynomial does a great job estimating. Now eventually what we're going to want to figure out is how far can I go out and still have it be a good estimate. Because typically when we're looking at a derivative or an integral, we're looking at a particular point or a range of points. So it's okay to be off clear out here at, let's say, 20 pi or something like that. It doesn't really matter clear out here at 20 pi. But where it does matter is right here in my area of interest. And so that's the thing that we're working on. We're trying to come up with that best polynomial to approximate that. Now again, I would create a chart. It's a little bit easier way to kind of work after these, because from the chart you can pull off your constants and keep track of your derivatives. Let's go ahead and look at another example, and then we'll also look at the very end, we'll look at error. And when we're talking about error, basically what we're saying is we're looking at absolute error. And when we're talking about absolute error, we're trying to approximate an actual value and see how much our approximation is off from the original value. Okay, so on this next one, let's go ahead and find the quadratic approximation. For f of x equals, this will bring back some fond memories here, product rule, x squared cosine of x centered at pi. And what we're looking at here, because we're centered at pi, we're looking at approximating this curve x squared cosine of x with a polynomial expression, and the quadratic approximation means second degree. So basically the thing I need to know here is I need to take two derivatives. And we're probably going to have to do some work on the side. So f of x equals x squared cosine of x. And then my first derivative, and I'll make my chart here after I have these derivatives and simplified, would be the first times the derivative of the second plus the second times the derivative of the first. So simplifying that, I'd end up with x squared cosine of x minus x squared sine of x. Now if I wanted to simplify this, I could. It looks like to me, whoops, I think I took a derivative wrong. The derivative of x squared is 2x. Here we go. So if I wanted to simplify this, I could pull out an x, but I'm just going to leave this. Now my second derivative, I'm going to have two product rules. I have a product rule of the first and then a product rule of the second. So my first product rule would be the first times the derivative of the second function, which is cosine of x, plus the second function times the derivative of 2x, which is 2. Okay, now continuing on, minus the first function times the derivative of the second function plus the second function times the derivative of x squared, which is 2x. So let's go ahead and simplify this one a little bit. So I get 2 cosine of x minus 2x sine of x, okay, minus x squared cosine of x minus 2x sine of x. Now if we can combine anything, that would probably be a good idea. It looks like we have a minus 2x sine of x, minus 2x sine of x, so I think we could combine those. So we have 2 cosine of x minus 4x sine of x minus x squared cosine of x. Okay, so those are my simplifieds. Now I'm going to go ahead and start my table. So my table is derivative, my center, and then evaluate. So my derivative, I'm going to start with f of x is x squared cosine of x. My first derivative, and that's right up here, would be 2x cosine of x minus x squared sine of x. Now you can see how quickly this can get out of hand. And so working with these derivatives, if we can just do it once and come up with this nice polynomial expression, I'll never have to do product rule, chain rule, quotient rule again, because I'll just have this nice little polynomial expression. I might have to do a chain rule. So far everything's been centered at 0, but this problem is centered at pi. So second derivative, 2 cosine of x minus 4x sine of x minus x squared cosine of x. And again, my center is at pi. So if I plug a pi in here, I'm going to have pi squared. Cosine pi is a -1. So this would be f of pi would be equal to negative pi squared. Now this one is pretty easy to do, straightforward, but the rest you have to probably plug in to see what's going on. So f prime at pi. So, gosh, these get so busy. So f prime at pi would be 2 pi cosine of pi minus pi squared sine of pi. And of course this would go to 0 because the sine of pi is 0. Cosine of pi is -1, so I'd be left with a -2 pi here. So I have a negative pi squared and -2 pi, and let's keep building on that. So that was my first derivative. Let's go ahead and look at my second derivative, evaluated at pi. So this is 2 cosine of pi minus 4 pi sine of pi, which goes to 0, minus x squared cosine of pi. Cosine of pi is -1, so I have -2 minus x squared. Cosine of pi is -1, so this is x squared minus 2. So again, you're going to have to show that. That's not something you can just do in your head real quick. You're going to want to write it down. So I have, not x squared minus pi, but pi squared minus pi, because I'm plugging in x equal pi. So pi squared minus 2. Okay, so here's our chart, and from the chart it's easier to put together our polynomial. In this particular case it's a second degree polynomial, so that's p2 of x. Now the way this works is f of c, x minus c to the 0 over 0 factorial, plus f prime at c, x minus c to the first over 1 factorial, plus the second derivative evaluated at c, x minus c to the second over 2 factorial. So I have p2 of x. Now remember, in our case, c is pi, so I'm going to go ahead and plug that in. F of pi, x minus pi to the 0, 0 factorial is 1. First derivative evaluated at pi, x minus pi to the first, 1 factorial is 1. The second derivative evaluated at pi, x minus pi to the second, 2 factorial is 2. So I have a good start here. p2 of x. F of pi, we know from up here, is a negative pi squared. X to the 0, x minus pi to the 0 is 1. So for my next term, f prime at pi is equal to a -2 pi times x minus pi. And of course, 1 dividing by 1 is just 1, so I'll leave that written out as is. Plus, the second derivative evaluated at pi would be pi squared minus 2, x minus pi quantity squared over 2. So this is my function. This is my second degree polynomial, and I could definitely simplify this quite a bit, but this is fine the way that it's written. So highest power would be right here, squared, and that will match the degree of the polynomial here as well. So this is my second degree polynomial that approximates x squared cosine of x. Now, if we want to look at our approximation here, this one's not all that easy to plug into our graphing utility, and I don't have Maple or anything. I'm just using one from online. So let's go ahead and look at x squared cosine of x. It's kind of an interesting graph. So there's x squared, and then we're going to have cosine of x. So there's x squared cosine of x. Now it looks pretty mild, but let's zoom out on this. This thing is really, really ugly. You wouldn't want to approximate this over the entire range of values. This is an oscillating function, it looks like to me. We have quite a bit going on here. I don't know where it peaks out on the end. I can see that near the origin it definitely peaks out. But here, I don't see it peaking out. It looks like to me that it's going to peak. It's just going to keep going up and up and up as we square those values. So we want to stay clear of this. We want to be near the origin. That's why we choose a value to be close. I'm going to go ahead and choose our steps by pi here. And let me see. So here's 5 pi. 5, 4, 3, 2, 1. So here's pi. I want to do a really good job of approximating what's going on right here at the center, and the center's right here at pi. So I'm going to see if I can get that pi to show. So again, the place I want to do a good job is right here at its center. And that's close to 3.14, should be 3.141. So that's real close to where I want to do a good job approximating. So if I look back on this, remember that was negative pi squared. And I'm just filling in my expression, minus 2 pi, x minus pi to the first. And I don't have to put to the first power. I can just put x minus pi plus, and then I have that pi squared minus 2. And sometimes when I look at these, I think, you know what? This really doesn't seem all that much easier than just working with that product rule a lot. But if we had to go to 4th degree polynomial, this would definitely be a lot easier in terms of taking derivatives and integrating. And the expression that I'm entering right now is just that approximation that we just found. And this is divided through by 2. Okay. So what we have here then is we have that this purple line is my approximation. The green line is the actual curve I'm trying to approximate. Now if we look at this near the 3.14, you can see that that purple line does a really good job of approximating the curve right along the green curve here. So this does a really good job of approximating at its center. In this case, the center is pi. It doesn't do such a great job everywhere else, but we don't care. We just wanted it to do a good job right in this particular area. I'm going to go ahead and take a screenshot of this and pop that into the lecture as well. So we kind of have a point of reference as to where we were working. Okay, so we've talked about quite a few different things. The process is not complicated. You guys have to keep track of a lot. Okay, and again, when the product rule, quotient rule, chain rule, all those types of things show up, make sure you're trying to keep that in a table. Make sure you're trying to keep track of those values because it can get out of hand pretty fast. Now, what do we do when we're trying to approximate the function evaluated at a particular value? That kind of changes everything. So for this problem, let's go ahead and approximate the cosine of 0.21, let's say. And this is in radians. And let's go ahead and do this with Taylor polynomials. And again, I have my choice. I could do 0, 1, 2, 3, 4, 5, nth degree, 10th degree. I'm going to do 3rd degree. So I'm going to do a 3rd degree Taylor polynomial. And then after I have this approximation, I'm going to compute the absolute error in the approximation. And I'll show you the formula that you'll need for that in a bit. So if I want to approximate the cosine of 0.21, I need to figure out a center. So 0.21 radians. Let's choose something that's easy to work with, something from the unit circle. And I can see pretty clearly that something near on the unit circle, something close to 0.21 would be 0. So I'm going to let the center equal 0 here. Now if that value is not given to you, you can choose your own center, but choose wisely. Choose simple values. So we want a third degree, so we need P3 of x. So that's going to be f of c, x minus c to the 0 over 0 factorial. And again, I know that most of this cancels into 1, but I want you to see the pattern because it's going to be very important that eventually we be able to very clearly and easily look at that pattern to figure out what's going on. So again, second degree polynomial. P3 of x. So f of c, oh wait, I forgot to do my table here. So let's go ahead and insert our table. So let's start here. Okay, so let's go ahead and look at our derivatives first, and then we'll work with this down here. So f of c would be the cosine of x. So I'm going to use the function cosine of x to approximate cosine, so that makes sense. Derivative f prime at c equals negative sine of x. Second degree polynomial would be the derivative of negative sine is a negative cosine of x. So these are my derivatives. These are my center. And these are my estimates. So this would be f of 0, f prime at 0, f double prime at 0. Now these are pretty easy. Cosine of 0 is 1. Negative sine of 0 is negative 1. Negative cosine of 0, whoops, negative sine of 0 would be 0. And negative cosine of 0 would be a negative 1. Now if it's anything more than a term or two, I would expect that you'd show your work. So let's use these to plug in down here. So f of c is 1. And of course x minus 0 to the 0 over 0 factorial. F prime at c is 0. X minus 0 to the first over 1 factorial. That whole term goes away. Plus the second derivative plus a negative 1, x minus c squared over 2 factorial. So we just want to keep simplifying this. And again, what happens here is this whole term goes to 0. Anything to the 0 power is 1. 0 factorial is 1. So this simplifies to just 1. And then over here I have a minus 1/2 x squared. So this is the third degree polynomial that approximates this entire curve. Now I need to take into account the 0.21 to figure out what's going on here. So what I'll do is I'll take P3 of 0.21. Because this polynomial will approximate the cosine now. Let me try and write that a little better. So I have 1 minus 1/2 times 0.21 quantity squared. Okay, so simplifying, we have 1 minus 1/2, and then I have the 0.21 quantity squared. 21 squared is 441, and then I'd move the decimal 4 places back, so that'd be 0.0441. Okay, continuing to simplify. I have a decimal and a fraction mix, which I don't like, but we'll figure that out. So I'd find a common denominator, 2 minus 0.00, so 0.441 all over 2. And then 2 minus 0.0441 would be 1.96, no wait, 1.95. And then 41 would be 559 all over 2. And then if we divide that out, this would be 0.9 times 2 is 18, remainder 1, 0.97795. So this is my approximation for cosine of 0.21 using this polynomial expression instead of the exact value. Because again, working with a polynomial is easier. Now, one thing we haven't addressed yet is absolute error. So let's go ahead and address absolute error within this problem. Now, absolute error is saying how far am I off from the actual value to the approximation. So we're just looking at a difference here. The formula for absolute error, let's go ahead and write that out formally because we haven't actually done one of these problems yet. But the formula for absolute error, as you might imagine, involves an absolute value. So it's going to be looking at the absolute value of my function So it's going to be looking at f of whatever my value is, in this case 0.21, minus my estimate Pn of x. So for this particular problem, in order to find absolute error, you basically need to know the value of cosine of 0.21 to know how far off you are. So for our problem, this would equal cosine 0.21 minus P3, we did P3 of 0.21. Now, to come up with your P3, this is doable to do this arithmetic by hand. It's not a big deal, and if it's on a test, it'll be very doable. You should be able to square some numbers and divide. Those aren't big things. This one, the absolute error, I would not expect you to be able to do on an exam unless some values were given to you. So looking up cosine of 0.21 radians, and you have to be pretty exacting with these because we're looking for the amount of error. So if we over round, we're introducing error. So that is the cosine of 0.21 radians. And then we subtract off what we just found, 0.97795. And it's going to be a positive number, so I don't really worry about the absolute value very much because the difference is already positive. And I get 0.000080914724148. And again, you don't want to round to the very end. We write our answers in scientific notation. So this would be 8.09 times 10 to the negative 10 to the negative 5. So this is my absolute error. So this stuff is not very difficult in terms of the process. Some of the derivatives get pretty intense, but they're very doable. So it's not a complicated concept, but some of the handwork is going to be. If you need to review your probabilities, your derivatives, product rule, and quotient rule, that might be a good idea. And then, of course, remembering how you're using these to approximate. A couple quick notes. If you're using a function to approximate, let me find a good example here. Let's say we're trying to approximate. So again, this is a different problem. I just want to point this out. So if it says to approximate the square root of 1.08, let's say, using the square root, using the function 1 plus x, note here, x is not 1.08, x is equal to 0.08. So the 1 is already there. So sometimes you'll have to look at the function you're using to approximate it and figure out what value of x makes it equivalent to the value we're trying to plug in. So be on the lookout for that because it can sometimes get a little bit complicated. As usual, if you have questions, please let me know. I'm happy to answer you via text. We can also set up online office hours if you'd like to work like that. And also remember that you do have the Pearson Connect to a tutor available to you 24/7. Good luck.